Hello. This video was prepared to provide background information regarding the flooding that has occurred over the last few years near the Bears Drain in Port Colborne, Ontario, and also to stimulate discussion of potential mitigation approaches. Let me begin by introducing myself. My name is John Schott. My family has owned property within steps of the Bears Drain for the last 75 years. I've got a lot of experience with the drain and all of its various manifestations. In addition to this, I studied stream flow and lake hydrodynamics as a graduate student and have published on lake hydrodynamics. Let's begin by recognizing that the flooding is not caused by rain events, but rather by what's called storm surge. This occurs when strong southwest winds take the water from the western end of Lake Erie and push it to the eastern end of Lake Erie, raising water levels dramatically at the eastern end and pushing water backwards up the drain and over the banks of the drain. This chart illustrates the storm surge concept, where if you look at the bottom, you'll see that on the right-hand side, which would be east in our case, the water levels in the lake can actually rise, generating what's called wind setup, or elevation of the waters at the eastern edge. And correspondingly, at the western edge, the water levels will drop. These events can occur very rapidly in a major storm, with the water levels rising by as much as a couple of meters. To characterize the data, I want to point out that if you look at the wind direction here and you look across perpendicular to the wind direction, you'll see that Port Colborne and Sturgeon Point are roughly the same location relative to the wind, just on opposite sides of the lake. So in many cases, I'll be showing you data from the U.S. station at Sturgeon Point, as well as occasionally the data from Port Colborne. Turns out the U.S. data is a little easier to access and also didn't fail during some of the major storms where the Port Colborne station periodically failed. This chart shows some plots that we're going to use regularly to describe this phenomena, so let me spend a couple seconds on them. The top left one here shows 6 days across the bottom axes, and water levels on the left-hand axis as recorded at a gauge station, water gauge station in Buffalo. And what you see is the lake starts out here at a little over 174 meters in elevation above sea level, and then the storm hits, the windstorm hits and pushes the water levels from the western basin up into the eastern basin at Buffalo to eventually 176.7 meters. So that's 2.5 or so meters higher than it started. And then over time, the winds slowly die off, very slowly in this case, and the water levels drop to, actually don't get back to normal until the next day after, beyond the chart here, December 26th. So this was a storm that took place just before and just after Christmas at the end of this 2022, and in many of my charts will refer to that as the Christmas storm. The next two charts over here on the right-hand side show the recordings from the U.S. stations at Sturgeon Point and the recordings from the Canadian station at Port Colborne. These data show, to begin with, that the storm starts at very nearly the same time, very slightly before, and that the peak is a little lower than Buffalo, a little less than half a meter at both Port Colborne and Sturgeon Point. They also show, if you look carefully, that the water levels at the two stations track nearly identically, both in height and in time. And again, this is because they're roughly opposite each other, opposite relative to the direction of the wind speed for a southwest storm. Most of our big storms are southwest storms, so that's what we're going to be referring to. And we're going to typically use the Sturgeon Point data just because it's a little easier to come by and handle. I want to point out one more really important thing on this plot. In addition to having the water being quite high, this stretch of time here, spans roughly 15 hours that the storm waters were at or above 175.75 meters. So this is water that's probably coming over the Bears Drain for, in this particular storm, a very long time of about 15 hours. Many of the other storms, the duration is quite a bit shorter. In these plots, we're showing 4 locations on Lake Erie for the Christmas storm over a 5-day period. We'll start in the bottom right, where we're looking at the data from Buffalo. We see that the water level starts just a little above 174 meters, rises rapidly with the storm, and then the water levels return to normal about December 26th. Buffalo is all the way at the eastern end of the lake. If we look back just a little bit to Sturgeon Point, we see again the wind set up this rapid rise in the lake level. Gets not quite to the same levels as Buffalo, almost a half a meter lower, and again decays over time. If we look a little further west on the lake, we see at Erie, Pennsylvania, the water levels rise quite a bit lower, over a meter below where they get to at Buffalo. And then finally, if we go way to the western end of the lake, we see what's called the wind set down. The water again starts just a little above 174 meters before the storm, and then the wind set down occurs and the water levels drop almost 3 meters. So we see a dramatic change from the storm surge, pushing the water levels up at one end and dropping them significantly at the other end. In this chart, I want to talk about what's called a seiche. It's often used in reference to storm surge, but it's slightly different, and I want to point out the differences. So when we've got a strong southwest wind, we push the water down to the eastern end of the lake. We get the wind set up, the high water that causes the flooding. And at the western end of the lake, we get the wind set down, which exposes beaches that may not normally be seen, for example. The storm surge is driven by the wind. It pushes the water down here, but you can imagine all that water down at one end of the lake pushes down. It causes pressure that pushes down on the lake and wants to push the water to start a current to return the water to the other end. This actually occurs when the wind finally stops and the water pushes back to the western end of the lake. This water coming down from the eastern end actually raises the water in the first return of the water in the storm surge, and it's a slosh. The water basically sloshes down to the other end of the lake, raises the water here, lowers it here, and then the opposite occurs. This water pressure wants to push the water back to the other end, and this is all attenuated over time, so it doesn't take very many sloshes before the lake to return pretty much to normal. Now, this is sort of an idealized case when the wind just stops abruptly. In many cases, the wind just dies down slowly, and you actually don't have the seiche occur quite so dramatically. In this part, I want to point out the variations in how water changes over time in the lake independent of the storm surge. So this is a 10-year plot, and what you see here is here's 1 year and here's the second year, and you see this sort of cyclic raising and lowering of the water level. It's usually about a half a meter or so over the course of a year, with the water higher in the spring, late spring and early summer, and then falls through the summer into the winter months. So you see a pattern here over not only a year, but also from early 2013, you see the water rising. It peaked in the early 2020s and has fallen back, not quite to normal, but at least approaching normal by the end of 2022. And here you see the little peak, which is the Christmas storm. In this slide, I want to show you these same plots, but over several different time periods, so we can see how we can find when storms occur and how severe they are. So the top chart is again the 10-year chart, and you can see the cycles as we pointed out the last time. And here you can see the Christmas storm, the end of 2022. A couple things to note though, it's just one little blip. You don't see much detail in it, and also it only goes up to 175.5, a little over that maybe. And that's because these are daily averages, and so the storms tend to get softened out. If we look down at the bottom right here, we see just a 1-year plot, and these are hourly data. And you see in the hourly data, the Christmas storm rises up to well over 176 meters. And the other thing to note that's important here is we get another storm over here in early January that doesn't even show up in the daily data, the daily average data. Over here, I'm looking in detail over just a couple-day period at this January storm, and you see indeed it's a pretty significant storm. The left-hand axis has a more exaggerated plot of heights of the water, but it gets up to about 178, almost 176 meters, 175.8 rather, almost 176 meters. And so you see, as this is a significant storm, it probably would have caused a little bit of flooding at the Bears Drain, but it's not quite as severe and it's not quite as high. So if we're going to look at these lake level data, this is all for Sturgeon Point, by the way. If we're going to look at these lake level data, we have to look at least the hourly data sets. These are on actually 6-minute samples to see the detail in the water. And we'll look at these in hourly data in the charts that follow. So in trying to understand why we're getting these flooding events now, I looked at annual data over several years. Here are 4 years. 2022 we already looked at, and these happen to be Buffalo data. And so what I did is I said, how often is the storm above 176 meters or significantly above? So if you look here, there's 176 in 2021, and there's one event here and another event here where we have water levels at Buffalo significantly above 176, over 175 in some cases. And those would probably be a few tenths of a meter lower at Port Colborne, but still storms that would probably have breached or overflowed the Bears Drain. In 2020, here's 176.5. So you've got 1, 2, maybe 3 storms of significance in 2020. 2019, here's 176.5 again up here, and you see 1, 2, maybe 3 storms of some significance in 2019. 2018, here's 176. None of the storms raised the water levels above 176 in 2018. And I didn't do an intensive search, but if I look back the few years previous to 2018, they look very similar. There are no storms higher than 176. And I should also point out that 2018 and 2019 are close to high lake levels. So even though the lake was quite high, the storm surge wasn't as severe. And so what we're seeing in 2019 and beyond, we're starting to see storm surge events that are extreme. And this all seems to be related to the fact we're now getting higher winds and extreme events all across the world, but certainly in the Lake Erie Basin, and it's generating these storm surge events that cause the flooding. So that was a lot of background material on the lake itself. And I want to talk a little bit more detail about the Bears Drain. So the Bears Drain is a drainage ditch that was designed to drain the low-lying areas back here. A hole was punched in the sand dune. The sand dune runs along the lake here in the late 1800s. So this drain, this brown line here, the root beer colored line, which we all know that Bears Drain is often referred to as Root Beer Creek, was established roughly in the late 1800s. In the late 1980s, early 1990s, The surge, the storm surge from the lake, was pushing water up the drain, flooding over the banks into the low-lying areas back in here, and particularly along the Wildwood Road. And the city undertook a study to determine what could be done to mitigate that flooding. And as a result, in the late 90s, actually 96, 97, work was done to mitigate the flooding caused by the overflow of the Bears Drain. And this work consisted of building a berm all along here and another one on this side to basically channelize the drain so it stayed inside. Back here, the banks of the drain were already high enough, they didn't need construction. But here, alongside the William Michael drain, the berm was added, and again here, and a tide flex valve, a one-way valve, was put in the Michael drain so that it would, under rain conditions, would let the water flow into the Bears Drain and out into the lake like it's supposed to. And when the drain was high, when the water was pushed back here by a storm, it would stop here and would be contained within these berms. I also want to point out down here, these are block walls that were built in 1981 to keep the banks, the sand dune, stabilized on either side where the drain punches through the sand dune. Also, I'll point out there's another tide flex valve here that was installed at this point, which lets the rain-generated water move through into the Bears Drain. So again, it's one way into the drain. And there's another one here on what's called the west branch of the Bears Drain near Fire Lane 9 that lets the water flow in from the west side into the Bears Drain during rain events and prevents the backup during a storm. This berm was built to a specification of 176.2 meters, which was determined to be what storm surges at the time looked like they would rise to roughly, and so this was slightly higher than the expected storm surges, and was designed to keep the water in the drain so it would rush up the drain, basically pool in here, be contained within here, and then when the lake dropped, it would flush back out. And this seemed to work for about 20 years when the storm surges stayed below 176-ish meters. Obviously, in more recent years, there's been problems. So as we've seen for the last several years, the storm surge at Port Colborne area has exceeded 176.2, the specified level for the elevation of the Bears Drain berms. It's also quite possible that these berms are no longer up to specified levels due to erosion and settling of the berm. I'm going to look at a particular storm to see the effects of the storm surge. We're going to use the December 11, 2021 storm because I happen to have a great deal of data of that. And as you can see here, it was a fairly significant storm reaching about 176.3 at Sturgeon Point. I'm not quite sure what the level at Port Colborne was because at this point in time, as the storm was reaching 176 meters, the Port Colborne recording system failed right through the peak of the storm. So we're going to use the Sturgeon Point data to illustrate this in a series of videos and pictures that I happen to have available from that storm. So here's a video showing the lake during a storm surge. This is the December 11, 21 storm surge. The camera is roughly here looking over the mouth of the Bears Drain. We're going to sweep from here over to here during the course of the video. So I've rotated this overhead image to put it in the same orientation as the picture to the right. And what you're seeing here is cameras here looking out over what should be a giant beach. The beach would normally extend like this out in this region. and the entire beach is underwater, and you see here a wave running up the Bears Drain, which sits back here. So the entire beach is underwater. This is early in the storm. The waves will eventually break over the walls and cause erosion back in here. This video is taken about 5 minutes after the previous one. It's at the end of fire lane 15 on the backside, the north side of the dune, looks at the berm and then sweeps across to the east. And what you're seeing is the water starting to come over the banks of the drain, and the water level in the lake is about 175.75 at this point at the recording stations. This video was taken about 20 minutes later. The lake level is now up to 176.2 at Port Colborne, and you can see that the water is well over the banks of the drain and flowing westward across the lots on fire lane 15, the back of the lots on fire lane 15, and will flow through the woods to along the Wildwood Road. One last picture. This is from the Christmas storm. Here's where the Bears Drain should be. This is all water flowing across the back lots of fire lane 15. This picture was taken at 9:38 in the morning. The recorded lake level at Port Colborne was 175.94, just under 176 meters. The peak of the storm was 0.3 of a meter or so higher. These numbers correspond, if you read down below, very closely with what was going on at Sturgeon Point. It's important to recognize that this Christmas storm was much more severe, not so much in the height of the lake, but the lake levels got high and stayed high for almost 15 hours. At Buffalo, the recorded wind speeds steady state were at about 40 miles per hour for those 15 hours, with gusts over 60 periodically during those 15 hours. This is the peak right here, this 15-hour period, and the lake, of course, took a couple days actually to settle down. When your property is being flooded, I think it's normal to want a quick solution. I'm afraid that this is a complicated problem that's only likely to get worse, and I'm not sure a quick, simple solution is going to solve the problem. I spent a little bit of time brainstorming some ideas for mitigating the problem of flooding, and some of these are harebrained, some of them are quite expensive, and I'm not a proponent without serious study of any of them, but I'll throw out a couple. I'm not going to go through all of these here in this video. But one quick solution is to raise the impacted properties or the buildings on them and let the floodwaters move around them and under them. The second one is basically the solution from 1996, which was to raise the existing berms, at least back up to where they were supposed to be, and probably need to be higher because of the higher storm levels. Another one is to raise the berms on the south end of the Bears Drain up to about where the West Bears Drain comes in, and build a flood control structure there. By the way, these flood control structures are often called gray structures because they're usually built out of stone or concrete. So in some of the notes that follow, you'll see a simple reference to a gray structure. By building a control structure farther away from the lake, it becomes a simpler structure because there's little wave action. The wave heights and energy have dissipated as you move further away from the lake. You'd still have to build up the berms south of any flood control structure to deal with the raised lake levels. There's a lot of other options in here that I'm going to skip over. The one that a lot of people jump on as a solution is to build a large gray structure near the mouth of the drain, where the city has already in 1981 built large masonry block walls to stabilize the dune on either side of the drain. This would be a very large structure and very costly, and it's certainly an option, not one I'm real fond of. I suspect what is needed is a serious engineering study to look at a range of options and maybe a combination of options to come up with a cost acceptable solution to mitigate the problem. A couple general issues that I hope will be considered in any planning going forward. The first one is that this flooding that is of concern at the moment is not typical rain-generated drainage problem. It is a storm surge problem, much more typical of what goes on in ocean coastal regions, and I would hope the engineers involved in the process would be people familiar with storm surge along coastal regions and behind coastal dunes. The second one is that the shape of the retaining walls that have been built to protect the dunes and the property along the lake all curve inward at the drain. This has a positive effect for the property owners in that the power of the storms is pushed to the side, and the water running along in front of the walls has less impact on erosion behind them. It also has the effect of channeling some of the storm surge up the drain so that there's more wave action up the drain. This has not been a problem since the berm was built, in that the surge was contained within the berm walls, but any structure that was located close to the lake would have to deal with the extra power from the waves and the storm surge running up the berm. This is naturally mitigated by the distance up the drain. I know there's been some interest in building a large structure at the mouth or near the mouth of the Bears Drain, and I've identified here a number of potential issues associated with that, cost being the largest one. And if the city is going to pursue something like this, I hope they take some of these issues into consideration. I'm not going to bother to go through all these issues here. I'd encourage you to stop the video and read them at your leisure, as well as with the previous slide. You can go back and stop it there and read those if you're interested. I'm going to close by saying I've studied water motion, hydrodynamics a lot in my career. I know the Bears Drain intimately, and with all that background and knowledge, I don't feel I know what the right answer is. I think it's going to take careful study to look at the problem and what the problem is going to evolve to over time, and try to come up with a well-designed solution. I hope this video has been of some use to you as you try to learn about and get involved with the drain issue.